Hi everyone. Today's guest is a friend and colleague of mine who is a real fountain of knowledge on all things structural engineering. His career has remained highly technically focused, and he's been involved in the delivery of some really complex and elegant design solutions. He works really closely with the construction teams to ensure the constructability of his designs while still meeting the demanding needs of clients and stakeholders. The topic that we're talking about today comes from Riccardo's characteristically holistic approach to solving a rather challenging element of a client's design brief. So he spotted an opportunity to optimise the benefits of differing material properties across a plate girder. He soon realised that there wasn't really enough design guidance out there for the particular application that he was looking to use it for, and so set about creating that guidance. I'm sure you'll see from our conversation that Riccardo is passionate about structural engineering and advancing his craft, and I hope you enjoy it as much as I did. Well, hi Riccardo, thank you so much for coming on the podcast today. I think we've got a really nice little technical topic to talk about. I'd like to try and make it accessible for as many of our listeners as we can. So I think if we start right at the top, and what do we actually mean by hybrid steel girders?
Yeah, first of all, thank you, Nick, for inviting me and talk to you about hybrid steel girder. And a hybrid steel girder is essentially a steel beam that has got two different grades of steel. So you could, as you fabricate the steel girders, you'll have webs and flanges. So you got an opportunity to mix the grades to the most efficient way. So that's what it is. And for a beam that works in flexure, in bending, you obviously got the highest bending stress at the top and bottom in the flanges. So that's why you could play a bit with the grades. Yeah, that's as simple as that.
Yeah. So what was your motivation to look at this? It feels like something we probably you would imagine has been looked at before, but I'm guessing perhaps not.
Well, it's definitely not a new concept. Yeah. And when I searched into it, I found that in the US or North America, they were doing that since the 1960s. They've been developing it. But the motivation that we found recently was because, as you know, the clients and our industry is trying to reduce carbon. So before, it was really looked at as an efficiency and a cost, reducing material cost. But in those days, the high strength steel, so grades above 355, were more expensive, and they still are more expensive. But in the last 20 years, the steel industry has moved quite a long way, and they can make those higher grade of steel in a more accessible way to us, to our industry. And essentially, we've been working on this National Highways project where there was a big target of carbon reduction. Yeah, and there was 5 steel concrete composite bridges that we were doing a deck replacement, and there's a target of carbon reduction, and that's kind of triggered me the idea, because I thought, how can I reduce carbon on a scheme that is quite set? And I thought, well, can we use higher grade of steel? And then the SCI published a good document in 2021 on high strength steel. So got me interested, and inside there was a hybrid girder, but not applicable to bridges. So that's got me research into it, and then basically that was the motivation. But in Europe, it's been a bit slow. The Swedish, they've done few road bridges using hybrid, but not elsewhere. And as far as I know, not in the UK on bridges.
The hybrid element of it, you mentioned about the cost of the higher grade steel being higher. Was that something that was immediately raised as a concern, or have you found that actually that problem's gone away? Because I know a lot of the steel we use is recycled, and I'd imagine if you've then got a pool of material you're going to recycle, which is of a higher grade, that presumably means your new products are immediately easier to have a higher grade out of them. Is that fair?
Yeah, it is fair. It's also fair that obviously, if you what the way we went to is using a 460 grade for the flanges and 355 for the webs and all the other elements. Yeah. So if you think on a plate girders for bridges, the tonnage, overall tonnage, is about 50-50 between the flanges and the rest. So if you can optimize the flanges, and if you think about just the yield ratio of the two, you're saving quite a bit. But the cost is only 15% more, while the yield gain is 30 or 35%. So you straight you got a net benefit, and then you have to straight away. But you have to design efficiently to make the most of it. Yeah. So yeah, and in terms of the recycled steel, so we contacted few suppliers. We contacted ArcelorMittal, and they do a steel called X-Carb. They've got a patented steel that is carbon efficient, if you like. But you cannot find S460 in that grade, but you can find S355. So potentially you can say, you know what, I'm going to use all my S355 from ArcelorMittal X-Carb, and then my S460 from somewhere else, and then you gain even more on a carbon, if you like. So yeah, the driving part of the looking into it was really to try to reduce carbon and make it cost neutral. So what we found is it wasn't more expensive overall because we reduced the tonnage overall. So yeah, it balances out, but it's a gain in carbon, purely the carbon.
Yeah. So you mentioned actually the missing link was the guidance for using it on bridges and specifically really in the UK. So what actually was missing, and what were you looking for guidance on?
Yeah, so what the SCI guide on high strength steel has got a design example, because the SCI are very good at putting examples, but they've got a design example for a beam in a building, non-composite. So that gives us the rules, which are actually set in the Eurocode Part 5 on plated structure. There is not a departure from standard. It is allowed in Eurocode, but Eurocode says you can do hybrid as long as the grade between the flanges and the web, the ratio of the two is not greater than 2. So if you use S460 and S355, you're well within that range. So that was ticking the box, we fine. And then say, okay, what happens then? There's some rules about checking the slenderness of the section, and you have to use the higher grade for the epsilon factor. So that makes you web potentially class 4. Yeah, because it plastifies. And then we say, okay, how do we go from that? We need to analyze as a class 4 section. There's a redistribution that's happening. So we started to look at some papers that were written. So you have to apply the structural engineering rules, but there's no clear example. So that's why it brought us to say, okay, we need to do something about it. We need to find our own procedures. How are we going to tackle this? And we checked also. We made sure that the SLS, for example, will remain within the elastic range. And that's not codified. That was something that we thought it was wise to do. And then we also decided that we would not change the span to depth ratio, the usual span to depth ratio for steel, concrete, composite. So we're not trying to reduce the depth of the girder. We're just going to optimize the flanges. So in terms of stiffness, we're not losing as much. But then we have to check the lateral torsional buckling because we got smaller flanges, we have more bracings. So you win some, you lose some, but you don't lose enough to counterbalance the overall benefits.
Yeah. You mentioned about the ratio of the grades not being greater than 2 difference. Do you think that's because of the variation in the elastic behavior of the material, or some of the properties that we rely on? I mean, the design codes make generalizations about behavior. We statistically analyze the variability. Presumably, if you go from an S275 up to a 460, for example, those statistical generalizations start to no longer overlap as much as you would like. Do you think that's the reason why?
Possibly is also, that plasticity region that we talked about. You basically cap the stress in the web to its yield, but you allow at ULS, you allow the flanges to go to his greater stress. So that suddenly that triangle of stress needs to redistribute somehow. So if you make that a bigger step, I guess you enter a domain that is probably beyond what the research has done. So the research, there's quite few people research, even within Europe, tested also for fatigue. So we on road bridges, the fatigue is a criteria, but is not as critical as for other railway bridges, for example. But all the fatigue for road bridges on hybrid has been found to be same rules and not governing, if you like. But yeah, I think that's why they put that limit. The two is becoming too dissimilar. I think maybe from a grade point of view.
Yeah, I can imagine there's also a danger that in order to reach anything close to the yield capacity of your flanges, you've already yielded your web and potentially started the strain is getting a little bit too high.
Yeah.
Okay, fair enough. So could you talk us through what the benefits were that you actually found on the particular project you were looking at? So I think you say there's some obvious advantages and a few where you actually it's a disadvantage, but they balance to a net benefit. So what did that look like in the end?
So we did a parametric study, and we using one in the SCI design example, and we also applied to our 5 bridges that we designed. And what we find on all of these, that we are between 10 to 12% overall reduction in steel tonnage, which correspond, because the EPD for S460 and S355, the declared APD is the same, is very similar. So you gain
the embodied carbon of the production of that.
Of the production, purely the production. Sorry. So basically, from that 10% overhaul, 10 to 12%, you gain that 10 to 12% carbon reduction on the structural steel. And that's the main advantage. Yes, the sections are a bit lighter to erect and transport, but that difference is going to be very small. There's no change on the substructure, things like that, or the bearing forces. The steel is not the big element there. So it is the main advantage is on the carbon, essentially.
And then you said the disadvantages were you needed a little bit of extra bracing. You presumably had to change your classification of the section. You have to revisit that a little bit.
That's right. So from a design point of view, we're putting more work on ourselves because when you do a conventional section, it could be S460 altogether or S355, you will follow just the simple rules. But with this, there's additional rules to follow. So from a design point of view, we had more to do, and then we needed more cross bracing. Increase the amount of cross bracing in the span.
Is it fair to say there's more design effort, even if you'd chosen that solution from the outset? And I can imagine it's obviously to change it is additional work. If you've picked up a scheme that's that, but you're saying it's still additional, it's still a bit more effort, design effort required, even if it's from the outset.
It's a little bit more, not drastically, but a little bit more. I will definitely recommend you to look at the method before you embark into it, so you don't waste any time.
Yeah. And you say that are there any other disadvantages that you came across? I mean, did you have pushback from suppliers and ability to weld different types of grades, and presumably efficiencies of ordering 2 different grades of steel? You've got a sheet of one grade, a sheet of another grade. You can't then nest your components quite so efficiently, and so on.
Yeah. So it's interesting because when we first considered that on that scheme, we asked the main contractor, "Can we speak to your current fabricator you've been talking to, and they were quite open. They say yes, we've done that before, and but this was a big international fabricator, and they agreed with us that yes, cost neutral for the grade that we were mixing, and the reason why cost neutral is the overall tonnage, but one disadvantage with the higher grade of steel, you need to be careful with some of the welding. And that's not the welding between dissimilar grades, because the welding between the web and the flanges is treated as for the lower grade material. So it's based on an S355. And that's okay. But for the shop welding of the flanges on the shop splices, which are full penetration butt weld, there's more there's more quality control to do for the higher grade of the steel. The more quality control is required, and is all to do with the heat control of the heat, the CV factor, but S460, I think is manageable, and as the bigger fabricator will say, yeah, we've done S460s. In fact, they're doing bridges with S460 already in the UK. There've been a couple of bridges, including a web and flanges. So that's the welding. So the big fabricators don't have an issue with it. The smaller fabricator, I did speak to a couple of them, and they will say, oh, no, we don't want to do that, because obviously for them is additional quality control requirements. So for them, they rather do something that is conventional. So yes, you need to check with your supply chain. You need to check on a particular project, if is it a good idea, or are we just making we're going to try to save something. Actually, we're not going to save carbon because we'll have to import it from further far away. Anyway, so that's the thing. But the other thing to watch out is now road bridges or plate girders for bridges are made in weathering steel where we can for whole life cost. And S460 in weathering steel in Europe, there's only one supplier. Yeah. So, for example, ArcelorMittal, when I spoke to them, they say, no, not quite there yet. Yeah. So it's Dillinger would be the supplier. And they say, yeah, no problem, we can supply, etc. So you need to make sure that this is taken into account by the contractor, the specialist fabricator in the lead time. Yeah, because so that's another thing to watch out is the supply chain. So I wouldn't say apply hybrid steel on all your road bridges. I would say check with your contractor, with your client, if it's appropriate.
It's that conversation. Do you get the impression that it's just a supply chain and gearing up the factories to be able to produce it problem, or is there a technical difficulty in actually getting that strength out of was it Core10, the weathering steel?
Weathering steel. Yeah. I don't know. I think ArcelorMittal will say, yes, we're working on it and we'll be there soon. But I think that because I think they put the efforts on the X carb. They put the effort on S355 X carb, super duper sustainability friendly. Maybe that's why, and maybe Dillinger didn't go that route. They say, we go for higher grade steel, weathering steel, because that's where we see the market be. So check the supply chain and check with your client.
So the project that you're talking about, that was a National Highways project, wasn't it? So were National Highways on board with this? Did they have any concerns, or were they really enthusiastic about this as a technical solution to their reducing the carbon footprint?
Yeah,
challenge?
So it was an interesting scheme because we were involved from the optioneering stage. We inherited schemes which impose steel concrete composite deck as a bridge deck replacement, but we had an opportunity to go back and to see at the arrangement, and then came the National Highways carbon team who say, you should save X amount of carbon on this scheme. So we were imposed that target, which I think it was in the order of 20% overall, which was very hard to do when you're just changing a deck, a bridge deck. So we looked at opportunity, and then we discussed with them when we found about hybrid girder, and we tested a little bit ourselves, and we said we think we can save some steel, structural steel. So we consulted the technical arm of National Highways, and we said it's included in the Eurocode Part 5 on the plated structure. Therefore, we don't think it's a departure. Would you have any objection for us to look into it? And they reviewed and they say, no, we got no objection. It's absolutely fine. You can pursue. So yeah, so we again, good point, Nick. You need to check with the technical approval authority before you embark into something that they might not be too familiar with, and they might be putting barrier. But in this instance, they were absolutely fine.
Yeah, yeah. Like one other thing that comes to mind is the subgrade. It's something that's caught me out a few times in the past, where you suddenly find that you make a small tweak to the steel that you're using. We're all familiar with the plate thickness sizes, and then doing your temperature checks on it and making sure your subgrade works, and then also that leading on to your fatigue checks. Presumably, as you step up the yield capacity of your steel, your subgrade goes up. That's something to keep an eye on. Did you find that was actually causing a challenge, or was the typical subgrades that are available usually enough?
It was enough. I mean, those plates in a higher grade that tend to be thermomechanically, the ML, NL range.
Yes.
Dillinger had all those subgrades available. So there was not an issue there. On our side, the Eurocode standards allow you to go with higher grade of steel. So those table for the thicknesses includes the higher steel. So we could use the same procedure, and because we can make the plates thinner, we didn't find any barrier on the subgrade selection of the flanges by using S460. Yeah, so that was okay.
Yeah, I think in the past I've always felt that the J2K2 is nominally the standard, and as soon as you start talking about M's, N's, you start raising a few eyebrows, a few questions as to, do we really need this? I'm getting the impression, as with higher grade steel becoming more available, those kind of higher subgrades are becoming more available and on the marketplace. Yeah,
that's right.
Is there any other particular areas of further research that you think is outstanding that people could start looking at?
Well, as I mentioned earlier on, there's a good SCI guide on high strength steel, SCI P432. I recommend people to, if they want to know a bit more about high strength steel with the limitations and application, etc., with some guide design examples at the back. That would be a good document to look at. In terms of research on hybrid, what would be nice to have is we published a paper that went to the IAPC Congress. My colleague went to present. So we got that paper, and then through the SCI Steel Bridge Group, there was an update to the structural steel for bridges guide P185, and we contacted them and we suggested they included something in a hybrid, and they did. So there's a new guidance note, which I think is 112. If you go to the 7th edition, you will find that gives a bit more information. But what would be good to have, I think, as we know as designer, is we like to have the equivalent of the SCI P356 and P357, which has got a nice go-to design guide, particularly for younger engineers, to say, okay, this is how you do it on a step-by-step basis. The NSC, if you look at the NSC magazine that's got some technical pages, they've written something already on non-composite girders. So you got those rules that we also followed. But I think it would be, in order to share that possibility as an option to the wider industry and to our colleagues, it would be useful if a proper guide would be written, I think.
Yeah, and is that something, if someone's used the hybrid steel, got a good set of calcs, is that something they can submit to the SCI, for example, for them to use as a working example? Is that how it works? Maybe you're not sure, but
Yeah, we could approach the SCI, and then we could recommend. I mean, we approach them for that guidance note, and see if there's any interest to write an actual guide. Yeah, we could do that. I mean, what we did for an actual design, we did because we already had the as you know, as usual, as Peter. Sometimes it takes time for clients to make decision. So we were proceeding on S355. So we had a preliminary design based on S355. And then suddenly the client says, no, it's okay. We can go for hybrid to save some carbon. Okay. So let's tweak the flanges. So we already had a design with S355. We did another design with S460 to compare the two. So our calcs will have to be written in a way that can be shared. Maybe we can use that because we did the parametric study on the previous two-span SCI bridge. So maybe we could use those calcs and submit them to the SCI for review and maybe publication. Yeah, it's a good idea actually.
Yeah, it's presumably about making sure they're in a generalized format and not too specific to one project.
Yeah.
And as a bit of a takeaway for people listening, when is hybrid steel definitely not the right answer? When is it just not worth considering?
Yeah, no, it's important. Yeah, very important question. I mentioned to you early on the fatigue. Yeah, if you got a fatigue at railway bridge, you know that the design is going to be governed from that stress range. So the fact you got a higher grade steel is not going to make any difference. So you will still have the same amount of material just to satisfy the fatigue. So you're not going to gain anything by using higher grade. So railway bridges, I will not consider hybrid. And a footbridge where you govern by deformation, oscillation, vibration, etc., where you need a stiffness. Again, you're not going to gain by making your section smaller. You're actually going to lose. So I would stick to the range of medium span or road bridges where the ULS is a governing criteria. So when the ULS is the governing criteria on flexural, then you have an opportunity to save material with hybrid girder. But otherwise, yeah. So it's a niche. Yeah,
it's a niche, and take away that you need to have a conversation with your client and your technical approval authority.
Yeah.
Check the supply chain, but there is an option there, and it sounds like there's a very real saving to be made, which is excellent because we've got this gargantuan challenge of how we reduce our footprint as an industry, haven't we? So it's just another little step along the way.
Yeah, definitely. And from us, from our point of view, it's always good to explore new avenues and to, from a pure technical and academical point of view, is interesting. But then, yes, from practical point of view, yes, it is a solution that can save you carbon if, as you said, if the whole chain of communication is satisfied. Yeah.
As you say, a happy coincidence that you ended up with two specimen designs effectively that you could do a compare and contrast against to actually confirm that we were making the benefit that we hoped we were, because it's not immediately obvious. Well, thank you very much for your time, Riccardo. It's been excellent. I think everyone should have learnt at least something from that and raised a bit of an awareness about what the options are for hybrid steel and how they can be used. So thank you. I'm going to put some information in the show notes about the various bits of guidance that you've referenced, if anybody wants to get some further information. But yeah, thank you very much for your time.
No, thank you much, Nick. Yeah, bye for now. Bye.
I hope you found that conversation useful and interesting. As I mentioned, I will be putting the links to the various pieces of guidance that we talked about into the show notes. So you have a look in there if you want to find some more information. I look forward to seeing you on the next episode.